Welcome everybody to Harmonic Analysis Seminar at UCI. It's our pleasure to have Alex Samorodnitsky from Hebrew University in Israel, who is going to talk about a moment ratio bound for polynomials on the Hamming cube. Please, Alex, feel free to start.
Yeah, so this is joint work with wait, something happened?
No.
Do you see it? Somehow,
yes, I see it.
I don't see it, wait. Somehow something happened.
Okay.
Yeah, good, I'm back. Right, so this is joint work with my co-author Naomi Kirshner. Right, and let me start with apologies. This is kind of funny. I will apologize to people who I think are interested in this, but anyway. So this was challenging because some of the audience might come from a different background. So again, I'm presenting, try to present a somewhat wider picture. And depending on my interests and why such questions are interesting. And so I think I have too much material. Maybe again, since there are a few people, and I'll be able to go quicker. So, either I'll have to go very quickly or not get to the proofs. So again, please stop me at any time. I really like questions and comments and so on, right? And in particular, if there is, since I really don't know continuous harmonic analysis, and if there are analogies or similar questions or insights one could get, I would be very happy to hear.
Mm-hmm.
Great. So here's a quick overview. So we get an almost tight upper bound on the ratio of the piece norm and the second norm of a function f when f is a polynomial of a given degree on the Boolean cube 0, 1 to 10. And we'll start with trying to present some reasons. I'm repeating myself why these questions are interesting to us. And again, great. So, and apologies in advance for some inaccuracies because I'll go quickly and I will cut corners and so on. Right. So, and then we'll describe our result and mention some applications. In particular, we'll describe a family. This we won't get to, but we will mention that we get a family of hypercontractive inequalities which take into account the concentration of function. Namely, we strengthen the classical hypercontractive inequalities for functions which are exponentially concentrated, say a characteristic function of a exponentially small subset of the cube. So for such functions, the hypercontractive inequality, the usual hypercontractive inequality is not tight, and we'll get an improvement, a tight improvement, in fact. Then we'll say something about the proof, and finally present some open questions. Right. So actually, the real order will first present some open questions and then talk about the proof. We'll have time. Okay. So let's start with describing harmonic analysis on the cube. So I probably will go quickly since through this material. So the Hamming cube is an additive group. It's a compact abelian group. So we have a harmonic analysis on it. It is also a metric space, which will be important to us, with the Hamming distance, which is just the L1 distance restricted to the cube, and it's also a product space, and it has many nice properties. So for us, we are the things we are interested in is the fact that it is a group, it has harmonic analysis, and its metric property. In particular, we'll speak about Hamming balls, namely the metric balls in this metric, and Hamming spheres, metric spheres in this metric. Okay, so we have a basis of characters, which is, so the dual group is isomorphic to because it's a commutative abelian group, to the group itself. So the dual group is also 0, 1 to the n, and it's indexed by the subsets of 1 to n, and the character for a subset S of 1 to n of the coordinates, the character ws at a point x in the cube, so x is a vector of length n of zeros and ones, it's just -1 to the power, which is the sum of the coordinates of x, lying in the set S, which can be also written as -1 to the power of the inner product of x and s, when one thinks about x as a vector of length n of zeros and ones, and also about s as a vector of length n of zeros and ones. Right? This is an orthonormal basis with respect to the usual inner product, to the normalized inner product over the cube, and we can expand every function via this basis, getting its Fourier coefficient. So f hat is the Fourier transform. right? And we have this Parseval's equalities that the L2 norms coincide in the Fourier domain and in the usual domain, right? This should be squared. The F2 norm squared is the sum of the Fourier coefficients squared. Okay. So let me give some examples quickly just to get some feeling of how does, Fourier transform look on the Boolean cube. If C is a subgroup, then then the Fourier transform with characteristic function, it basically is a characteristic function of the orthogonal subspace. C is also a subspace over the field with two elements. So we get that the Fourier transform of the characteristic function of C is a normalized characteristic function of C dual. Right, and the thing which will be most interesting for us is the following condition. We are looking at functions f whose Fourier coefficients vanish for all sets which are larger than some threshold d plus 1. And this happens, we claim that this happens if and only if f is a restriction of a real valued polynomial, the n-variate real valued polynomial to the Boolean cube. And let me quickly say why this is true. First of all, because the characters themselves are multilinear polynomials. Multilinear meaning every variable appears in degree either with degree 1 or doesn't appear at all. And this is very easy to see if you look at the upper line which defines this double S of x. I've added another expression. This is just a product over I and S 1 minus 2xi. So this is a multilinear polynomial, a real polynomial. And right, so the characters are all multilinear. And also because when we restrict a general polynomial, not necessarily a multilinear one, so the powers of x could be larger than 1 to the cube, we basically divide it by the ideal. In the cube, we have xi squared equals xi. So we divide this, this ring of polynomials by this ideal, and all the powers vanish. So all the powers greater than 2. Okay, this is very quickly just by hand waving, but this is an explanation why this harmonic analysis condition that all the Fourier coefficients for s greater than d plus 1 vanish if and only if f is a polynomial. So we'll call f degree d. So we'll call such functions polynomials of degree d. Okay, good. So we have this, and again, right, I'm going rather quickly, I think, but maybe, if you know it, then it's easy. If not, please ask questions. So for instance, if the Fourier transform of f is 1 on all sets of cardinality 1 and 0 everywhere else, then f of x has a simple expression. This is m times minus twice the sum of all the coefficients of x, of all the coordinates of x. In other words, this function is just the sum of all Fourier characters which are supported on sets of cardinality 1 on singletons. And this is also, for some people are used to call it some of the RIs, where RIs are the Rademacher functions. So Ri is just a special name for W for the whole Fourier character at a set of cardinality 1. And these are, very simple functions. Okay, good. So what are the questions we are interested in? So generic question, we have a subset of 0, 1 to the n, and we're looking at the subspace of the vector space of functions whose Fourier support is supported on A. So for functions whose Fourier transform vanishes on sets which are not in A. Right, and then for this subspace, we want to estimate the maximal ratio of norms, FQ over FP, where Q is larger than P. Right, this is a very general question. This is a difficult question. But many special cases were considered in analysis, discrete math, and information theory. Right, so let's speak about analysis. I feel kind of funny, right? Because explaining this, because at least Pata definitely knows this better than me. So, and I guess Jonathan, being a student, should I just skip over this quickly?
Oh, you can briefly say that.
Yeah,
so
briefly touch on it.
Yeah, so I'll go quickly. So, this is the classical inequality of Khinchine from 1923. That if the set A are the Fourier support consists only of sets of cardinality 1, which means just this vector space is a span of the Rademacher functions, then this norm ratio is bounded by an absolute constant, which depends on the norms on P and Q. Right. So in general, therefore, we'll sort of connect to it and we'll call any such questions Khinchine-type questions, just for this talk. Right. So, and actually people do call it generally Khinchine-type questions. And the exact values of the constants are known. In particular, if we look at the ratio of the second and the first norms, the exact constant in square root 2, due to Sharek from 76. And this is tight if f is the sum of two Rademacher functions. So what happens if A is all these sets of cardinality 2? So let's just connect to the metric on the cube. This is the Hamming sphere of radius 2, right? All the points in the cube at distance precisely 2 from 0. This is the Hamming sphere of radius 2 around 0.
Mm-hmm.
Right. So this is the question we want to look at. And Pelczynski asked whether this ratio of the second and the first norm is bounded by 2 now, not square root 2, 2. If yes, this would be tight for the following product function, R1 plus R2 times R3 plus R4. And this is open. And of course, one can go further, right? One can ask about Hamming spheres of radius D for general D. And the question is the best ratio 2 to the D over 2? Again, this would be tight by taking the corresponding product function. This is open, and best estimates for range of parameters are due to Ashkenazis and Pata from last year. What about general norms? P smaller than Q and general D. Again, open, and best estimates again are due to Pata and Koch. Great. So in general, the radius of the sphere we're looking at can go between D and N. But usually people in this area are looking at constant D or D increasing slowly with dimension. This is the interesting range of parameters. So I wonder why, by the way. Why didn't people look at the general D? This is a question to the audience.
No, I don't know. Usually polynomials appear more often than homogeneous functions.
Right. So polynomials of constant degree.
But decreases with n, right?
Right. But why people? So I think people analysis mostly looked at small d.
Yes, for fixed d, because I don't know. One reason is okay. I don't know if it is correct reason, but for functions, degree D Boolean function, fixed D, it is complexity which coincides with many other complexities like sensitivity, block sensitivity, decision tree.
Right. No. This is about like computer science. This I know, but I wonder about people in analysis. So Khinchine didn't know about sensitivity and block sensitivity, right?
Yes. But no, I don't have an explanation why 5 is.
Right. No, again, interesting, but yeah, I don't know. Okay, good. So anyway, but this is sort of the regime. This is the range of parameters people in analysis seem to look at. Right. So let's now speak about combinatorics and theoretical CS. Let me give you one result, which sort of describes one important result, which sort of describes why questions of this form became interesting. And this is, I think, maybe even the first non-trivial application of harmonic analysis in discrete mathematics, on the Boolean cube. So Alex, the claim is, yeah.
I wanted to say that another reason they look for fixed D, because sometimes we are interested to get bounds on the Hamming cube, which is independent of n, independent of dimension.
I understand. Okay, I understand. Right. So you want something independent of dimension, and then, yes. Right. I was also thinking about somehow, in my mind, this was vaguely connected to the fact, to this theorem of Dvoretsky, that, that the cube has this log n, sort of subspace, which is sort of similar to the Euclidean bow. But yeah, yeah, right. Okay. So right. So let me tell about Kankala and lineal. So this is the result. This is the claim, which I will explain at least a bit. So every balanced Boolean function has an influential variable. So what does it mean? So we have the Hamming cube, and we're looking at a very large subset of this cube, which is proportional to the cube, right? Its cardinality is some constant times the cardinality of the whole cube. And look at this characteristic function. Now the claim is that there exists a direction, one of the coordinates, right? For which, if we look at the function f, we are looking at the probability over all points x in the cube. So always when you speak about probabilities or expectations and so on, this is a uniform distribution of the cube in this talk. So right, so we're looking at the probabilities at a point, the function f at a point x is different from a function f at an adjacent point. We only change the i's coordinate. Right, so we're looking at two adjacent points in the cube, only change one coordinate. And we're asking what's the probability the function changes its value. And the claim is that this probability is small, but not very small. It's lower bounded by log n over n up to some constant. And the log n is the interesting part because 1 over n is very easy to get. 1 over n comes from some simple isoperimetric inequality on the cube. Right. So why is this so important? So let me say that historically, this was a very influential paper. Many things came out of this paper. People continued in different directions. So here is a corollary. Think about this function as describing some voting game. So we have n voters, which vote either 0 or 1. And the value of the function is this outcome of this voting process. And of course, we want this function to be balanced. So, for basically half of the votes, the outcome will be 1, and for half, the outcome will be different. The outcome will be 0. But this claim says that we have, in every balanced selection game, there is a dominating set of players of cardinality little o of n, basically n over log n. Because each player, given the votes of the other players, can change the game in log n over n places. And when you iterate this result, you get this interesting fact. So this was the original motivation of this paper.
Alex, just a small remark. I think you want monotone function in this corollary, right?
Oh, yeah, monotone definitely. But why do you need monotone? I just want to.
Because the way you most influential variables in next time.
You're right. Sorry, I apologize. Of course, if the function is parity, then yeah, right. Yeah, I want a monotone function. Sure. Thank you. So a monotone function is a function which increases when we increase the number of ones in the vector x. Right. So, and developing this approach led to many things. In particular, one can see if one looks at monotone functions, one can look at sharp thresholds for graph properties. This is a very non-trivial development, but sort of intuitively, suppose our input x, which is vector of zeros and ones, describes a graph. So, the coordinates are the edges of this graph, which edges this graph has. And the function is 1 if the graph has a certain property, a monotone property, and 0 no, if not. So we can see that we can change a few coordinates and get from 0 to 1, from not having a property to having a property. And this is the sharp threshold. And there are very delicate notions and stronger notions, but somehow one can see the general direction here. Right. So let's prove it. Let's give a very brief sketch of the proof of this result. So look at the difference function. Define f sub a of x is like a discrete derivative. Is a function of x plus ei minus f of x. So the difference between those two disjoint, the values of f at two adjacent points. So this function gets values -1, 0, and 1, because f gets values 0 and 1. And therefore, its L2 norm squared is exactly the probability that we want to bound from below. The probability that f of x is different from f of x plus e. So assume towards contradiction that all these norms, all these probabilities are all little of log n over n. Then the key claim is that almost all of the norm of fi is attained on the sort of the Fourier norm, is attained on characters, the characters which belong to sets S with S larger large. So let me say it more precisely. So the sum of the squares of the Fourier coefficients of fi on sets of cardinality larger than some constant times log n is greater than almost all the norm up to the small error. Is this clear? I mean, this is quick. If you know it, you know it. If you don't, this might be too quick. Any questions?
What is little
No.
alpha?
Sorry?
Alpha, what is alpha?
Alpha is some constant. I should have said. Alpha is some constant. Okay. So if we have this, we can sum over all I and use the fact that fi's have a very simple Fourier expression. This is basically very closely connected to the Fourier expansion of f itself. This is just a sum over all sets such as I belongs to S. F hat at SWS. So it basically keeps all the Fourier coefficients of f on sets S, which include I. And we also use the fact that our f, our original function, is a characteristic function of a constant fraction of the cube. So its L2 norm is large. And very simple, algebra gives us that the sum of the L2 norms of all these FIs is greater than log n. And this is a contradiction to the fact that we have assumed that all of them are all little of log n. And this is the proof. This is the proof of KKL, given this fact which I've written in purple, that if you have a function with small support, that almost all of its L2 norm, the Fourier of its Fourier L2 norm is attained in rather large sets. So notice that this can be viewed as an uncertainty type result. Because f has like a small support, f hat has a large support. It can be concentrated on balls of radius smaller than log n. Does it make sense?
Yes, yes.
Okay, good. So this is contradiction. And the key claim, this claim in purple, follows from the hypercontractive inequality on 0, 1 to n. This was the first application, as far as I know, this inequality in discrete math. So let me tell you what hypercontractivity is. So hypercontractivity and Khinchine-type questions. So let us first, so hypercontractivity tells us about how noise decreases norms. So we have this noise operator. This is a linear operator on functions on the Boolean cube, which sort of flattens the function out, decreases its norms. So here is definition is rather long, so let me say it. So we have this noise parameter epsilon, and we have for each epsilon, there is this noise operator T of epsilon, which acts as follows. I have a function f, I want to tell you what T epsilon of f is. That's another function. Its value at a point x is the expected value of f at a random point y, where y is obtained from x as follows. I flip every coordinate of x independently with probability epsilon, and I keep it the same as probability 1 minus epsilon. So this is sort of describing this in words. One can write the exact expression, which might help or might not help. Maybe also usefully, this is a convolution operator. So T epsilon of f is just f convolution with some noise kernel, which I will tell you what it is. This is this simple looking function, a symmetric function. Lambda epsilon at x depends only on this Hamming norm of x. This expression is the absolute value of x. I mean, you can think about the L1 norm of x is the number of ones in x, or a distance between x and 0. Right? So the value of this kernel at x depends only on the cardinality of x, the distance from 0. Right. So, and these operators T epsilon form a semigroup, which is an example of the heat semigroups, for the cube. So we had this hypercontractive inequality, a very famous one, proved by many people independently. And it says the following. So for any q and for any epsilon, the q norm of the noisy version of this noise operator applied to f is smaller than a smaller norm of the original function. So the larger norm of T epsilon f is smaller than the smaller norm of the original function. This is why this is called hypercontractive. Right. And again, this quantifies the decrease of norms under noise. We apply noise, the function flattens, the norm decreases. And since this is a convolution operator, it has a very simple expression. By a Fourier analysis, it's a multiplier. We multiply every Fourier coefficient by this quantity. This is T epsilon of f. So we get the Fourier coefficients of f itself, but multiplied by this exponentially decreasing factor. Okay? Great. So this tells us that if the second norm of f decreases sharply under noise, that the L2 norm of f has to be attained in large sets. And if the support of f is small, if f is a 0, 1 function supported on a small set, its L2 norm clearly decreases sharply under noise, and then we are done. And this proves the KKL inequality. Okay, this ends this sketch. Questions about this? Okay, good. So, so let us now connect this hypercontractive inequality to Khinchine-type estimates. So it's easy to see, and I won't go into details, that we have this hypercontractive inequality is equivalent to the following sequence of Khinchine-type estimates for functions, whose Fourier transform supported on spheres of radii d between 0 and n. Right. So let's fix d between 0 and n. Let f be a function whose Fourier transform is supported in a sphere of radius d in A. Then the ratio of q's and p's norm of f for q larger than p is bounded by this ratio, q minus 1 over p minus 1 to d over 2. So this follows immediately from hypercontractivity by applying the hypercontractive inequality to this f. And the other direction is also true, the inverse direction. If this ratio, if this inequality we know for all d, we can deduce hypercontractive inequality very easily. Great, so this is equivalent. Okay, so the next question is, are these inequalities tight for all d? Is a hypercontractive inequality itself tight, and are these inequalities tight for all d? Right, so let's start with the hypercontractive inequality, and the answer is yes, in the sense that we cannot replace the norm on the right-hand side by any smaller one. And in fact, it is essentially tight for almost flat functions. For functions, let's say for characteristic functions of very large sets in the cube. Great. So as I said, the set of all subsets of cardinality d, we call a Hamming sphere of radius d. And then one can ask, are these Khinchine-type estimates tight for all values of d? And from now on, we will speak only we will restrict ourselves to p equals 2. So the hypercontractive inequality for the Euclidean norm. And this is for two reasons. First of all, this is all we know, at least in this talk. And second of all, this might be one of the most useful, special cases, because we can deal with the Euclidean norm. So in this case, the answer is yes. These inequalities are tight if d is up to a constant times square root n, are tight up to some vanishing error, and no if d is much larger than square root of n. And the question is this interesting? Because in analysis and discrete math applications, usually people look actually, in fact, up to square root n. For d up to square root n. And in the KKL result, as we have seen, we are interested in d up to about log n, logarithmic n. And the reason is because the functions we are looking at, are almost balanced. The ratio between, say, the second and first norm is bounded by some polynomial in the dimension. These are the functions people in computer science, in discrete math, and maybe in analysis are most interested in. And then the Fourier transforms, the crucial part, is looking at rather small Fourier coefficients, in many cases. However, this is not the case in information theory, and let me go to information theory. So this is another area, right? And here we are actually interested in exponentially small sets. So interested in exponentially small subsets of the cube. And also we're by specific, a special interesting case, and this special case are linear codes. Very small subsets of the cube, which are also linear subspaces. And then the rate of the code is this constant multiplying n. This is between 0 and 1. Let's say if r equals 1/2, we are interested in linear subspaces of dimension n over 2, which are of course exponentially a small set. And these subsets have to have special structure to allow error correction. So the idea is we are sending our a sequence of bits, a point in 0, 1 to the n, sequence of n bits through a noisy channel. The sequence changes, and we want to recover it after this noisy channel. Right? There are many different models of noise. We'll describe two, especially the first one. So the first model is the famous binary symmetric channel. The input to this channel are binary sequences of length n, and the channel flips each bit independently with probability epsilon. So we have already seen it, right? So if the output distribution, if the input distribution on the inputs is some distribution f on the Boolean cube, then the output distribution is just t epsilon of it, right? So applies the noise operator we have seen in analysis. And now people in information theory are interested of how the uncertainty of a distribution is increased under noise, right? So we have some entropy of distribution before. Now we go, through this noisy channel, the entropy increases. We want to quantify this. Equivalently, how the concentration of function is decreased. Right, so let me speak about how people in information theory measure concentrational function. In analysis, the concentrational function is measured by its norms. Suppose we normalize the first norm to be 1, then for larger norms, the higher the normal function is, sort of the intuitively the more concentrated f is. And in this sense, hypercontractive inequality again measures the decrease of concentration under noise. In information theory, the concentration is measured by Shannon entropy. Actually, it's the anti-concentration. And we describe a closely related notion here, which is called the nth of a function. This is closely related to the Shannon entropy. But this is expression. Given a non-negative function, we look at nth of f. There is this expectation of f ln f minus expectation of f ln the expectation of f. This is a well-known notion in analysis. It enters into the logarithmic Sobolev inequalities, which in particular were used by Gross to give his proof of the hypercontractive inequality, and so on. So this is a convex homogeneous functional on non-negative function, and it is decreased, and therefore it's decreased under noise. This is very, similar to norms. And here is a very famous result from from information theory with this funny name, Mrs. Gerber's lemma. Note that it was proved in 73, basically in the same years as people were proving hypercontractive inequalities in analysis. So let f be a non-negative function on the cube or a distribution. Then the entropy of the noisy version of f is bounded by this explicit expression on the right-hand side, where psi is this explicit concave function in x in this first argument. This is a strong result measuring the decrease in concentration of a function under noise. And in fact, it's stronger for highly concentrated functions because of the fact that this function psi is increasing and concave. And this is stronger than hypercontractivity in a sense. This the more concentrated function is, the stronger this result is. And in fact, one can write a similar inequality. One can take a limit of hypercontractive inequalities because this nth is approximated by norms, and one gets a weaker inequality. And again, this is because people in analysis were mostly interested in almost flat functions, not exponentially concentrated functions. And people in information theory were interested in exponentially concentrated functions.
Alex, can I ask a question?
Sure. Yeah.
Do these people know about hypercontractive inequalities in that year? Or these words
I have no idea. So I think people in information theory claim that everything is independent. That in fact, people in information theory had an even earlier result by Alsvede and Gax. There is something called the strong data processing inequalities. And the first one was proved, I think, in 1969. And this is also like a first example of something like hypercontractivity.
Okay.
This seems to be independent. Right. And again, this is somewhat stronger than hypercontractivity. Is stronger because it takes into account the concentrational function. So the question is, can we have similar improvement for hypercontractivity? And the answer is yes. Let me describe some results. So assume now that our function is exponentially concentrated. The ratio of the second and the first norm, say, is exponentially large. For instance, f is a characteristic function of an error-correcting code. Then, together with Yuri Polanski, we proved some stronger hypercontractive inequalities for such functions. And one application of this is an uncertain type result for the Boolean cube, which I'll describe very briefly. And this can be applied to error-correcting codes. So again, recall that the key claim, of KKL was that a function whose support is a bit small, is of cardinality 2 to the n over n, has to attain most of its L2 Fourier norm outside a Hamming-Ball of radius log n. Equivalently, one can say it in words that the Fourier transform of a function with small support, small here is not very small, cannot be concentrated in a Hamming-Ball of a small radius, and small here is small, it's logarithmic. So what we proved, so alpha here is a constant. If the support of f is exponentially small, right, is 2 to the alpha n for some alpha between 0 and 1, then f cannot attain most of its L2 Fourier norm in a Hamming-Ball of a linear in n radius, some function of alpha times n, and this is tight. This function, is written explicitly somehow. It depends on entropy and alpha and some other things. So this is a tight result, and note that the parameters are very different. Now the supported exponential is small, and the radius of the ball is linear in n. Okay, great. And of course, this sort of should lead us, and it didn't lead us in that paper, but to the Khinchine-type questions when A is a Hamming sphere or Hamming ball of linear in n radius. Okay. And our main result in this talk is tight bounds for Khinchine-type questions where A is a Hamming sphere or a ball of linear in n radius. And this implies tight hypercontractive inequalities for exponentially constructed functions. And there are some applications which I won't talk about. And there's also some other papers which give different versions of, of these inequalities and so on, expand them and, more general versions and slightly different versions and so on. Okay. So, and Yuri Polyansky told me, in a conversation, that he has a more general family of tight hypercontractive inequalities, but so far this hasn't been published, so I'm not sure. I mean, great. Okay, so let me mention very briefly. And so, Pata, how much time do I have, by the way?
You have, okay, you can speak 15 minutes or more if you want.
Yeah, so I probably need something like 15 or 20 minutes. Let's say, I hope I'll mention 15 minutes. Okay. So let me very briefly present a Khinchine-type question of a different nature. So far, we're talking about functions whose Fourier transform is supported on a Hamming sphere or on a Hamming ball. So there are different questions. Let me briefly describe one which I like. So here is a different model of noise and information theory. Now the noisy channel maliciously flips some R out of n input bits, and the channel decides what to flip. It's not independent. This is stronger noise, like a worse noise. The only way to deal with this noise is to construct an error correcting code with distance to r plus 1, namely a subset of 0, 1 to the n with all its distinct points, at least distance d from each other, right? Each 2 points are very far from each other. And equivalently, this is equivalent to a disjoint packing of metric balls, of Hamming balls of radius r in the cube. And a basic question in coding theory: how large can such a packing be? And this is very closely related to, this is a central open problem in coding theory, and very closely related to the sphere packing problem in Rn. In fact, the best bounds for the sphere packing problems are obtained using this linear programming approach, adapting a proof from the coding theory. Okay. And the best known bounds are due to McAleese, Rodemisch, Ramsey, and Welch from 77, more than 40 years ago. And here's a conjecture from this year. This is a Khinchine-type conjecture, which, if true, would lead to improvement of these bounds. So I will state this conjecture only for linear codes because it's simpler to state. It can be stated for general codes as well. So let's see a linear code of minimal distance, which is linear in n. This is the most interesting range of parameters in coding theory. And let me say that the estimates, the packing, so linear codes correspond to lattices in the Euclidean space. And exactly as in the Euclidean space, we don't have better bounds for lattice packings than for general packings. Here also, we don't have better bounds for general packings than for linear packings. So the bounds are very interesting for linear codes as well. So let A be the set of points of weight exactly D in C. So the minimal distance in C is D. C is a linear subspace, so it contains 0. So 0 is in C, and I'm looking at points which are exactly a distance D in C. This is a dispersed set of points, right? There are distance at least D from each other, and also a distance D from C. Then the claim is, if we look at this ratio of the fourth and the second norm of a function whose Fourier support is supported in this set A, this ratio is sub-exponential. It's like this set is, right? They're kind of independent at this point. This is sort of the intuition. Right, so there is a history of this conjecture, which I won't go into. But anyway, it's interesting because if it's true, then we can improve the linear program. So here
Alex,
is
can you clarify again? So A is a subset of C, right?
A is a subset of points in a linear code, right? And there are minimal weight in this code.
Ah,
Okay. Okay, of weight D, right? So these are points whose in the linear combination they are exactly D1s, right? That's what you want to say.
No. Wait, no. This is the points in right. So the code is linear, right? The code, but the code is a subset of vectors in 0, 1 to n, right? It's just closed under addition. This, this is
okay. Weight D Hamming weight. Okay, I see.
Yeah, Hamming weight.
So, sorry. Yes, now okay.
So this is a metric information. This is metric information. So this points a distance exactly D from 0.
Okay.
In the code, right? So, and you want to say that in some sense this is a pseudo-random set in some sense. So this ratio is small. Let me just say that. Well, never mind. There is a history, but I won't go into it. Anyway, this is a different, right? This is a different Khinchine-type question, but let me. Right. So here, let me finally speak about our main results. So I recall that the classical hypercontractive inequality, and I write this inequality for 2 for the Euclidean norm, is equivalent to the following sequence of Khinchine-type estimates. Let D run between 1 and n/2. Let AD be the Hamming sphere of radius D. Then the maximal ratio of the piece norm and the second norm, P is greater than 2, is at most P minus 1 to the power D over 2. So this is equivalent. If this holds for all D, this is equivalent to the hypercontractive inequality. Let me write the same bound in a different way. Let phi be this following function. So P runs between 2 and infinity, and X is between 0 and 1/2. And this is just, log of P minus 1 divided by 2 times X. And the whole point is that P minus 1 to the power D over 2 can be written in this form. This is 2 to the exponent phi of P and D over n times n. This is trivial to check. So basically our bound is of this form. Now what we prove, our main result is that we can replace this phi by a smaller function. Let me call it phi. This is an explicit function, and it's always smaller than phi. Right, so this is our main result. So this is a tight bound. This is a better bound, and this is also almost tight for the function f, which is a very special form. This is just the sum of all the Fourier characters of weight exactly d. Let's call it kd. And the multiplicative error is actually quite small. Let me flash it and go on. This function kd is symmetric. It depends only at a point x. It depends only on the number of ones in x. In fact, its value at a point x is a value of some univirtual polynomial of degree d. At the integer, it's a real number, which is the cardinality of x, the number of ones in x. And these are exactly the zonal spherical function of the Laplacian of the cube, right? There is a group of symmetries acting and so on, and right, just to say it. And these polynomials k tilde d, which we will be using notation also called kds, as a family of orthogonal polynomials with respect to a discrete measure on 0 to n, these are called the Kravchuk polynomials. And we know a lot about them. They have been well researched. And we also don't know many things about them, but we also know a lot of things about them. Right. So let me start before say something about the proof. Let me quickly pose some open questions. So we know that these functions kd almost attain the maximum ratio. The question is the maximum ratio question. The question is whether they actually do attain the real maximum. And for p equals 4, this was conjectured by Kirchner and myself in an earlier paper, and it was proved by Aronson by a very nice argument, which can be easily extended to the case where p is an even integer. And this recovers the same result of Larson-Kohn from 0, 2 for the Hermite polynomials, as Sparta pointed out to me. And the Larson-Kohn also asked the same question about general p. So the cube situation is more general than the Gaussian space situation, because the cube models the Gaussian space. So whatever we prove for the cube, we can also, by some limit argument, prove for the Gaussian space. Okay, so here, this is one question. The other question is this phenomenon of the zonal spherical functions maximizing the norm ratio holds for other very symmetric spaces? So for instance, the Hamming sphere, this is a very symmetric space, and the zonal spherical functions are defined by another family of orthogonal polynomials, the Hahn polynomials. or the Euclidean sphere when we have the Jacobi polynomials. In fact, when one works on packings, one can see that all these spaces behave in a very similar way. So it wouldn't be very surprising if the same thing holds for all these spaces. In particular, this would be interesting. First of all, this would be an interesting phenomenon. And also, this might lead to hypercontractive inequalities for these spaces, which I'm not, at least for the Hamming sphere, it is unknown. In fact, people working on that ran into some difficulties. There are some difficulties with the Hamming sphere. But so it might be interesting. Let me also mention that, proving our Khinchine-type result leads, and I won't speak about this, to another proof of hypercontractivity, which seems to be different from the known proofs since it does not directly use the product structure of the Hamming cube. The known proofs use tensorization. The proof is something for the 2-point space and then tensorize because the cube is a product space. And here it's a different approach which might extend to a non-product spaces, actually like the sphere as the spheres. Okay, good. So these are the open questions. Questions about the open questions.
Leading to proof of hypercontractivities, you mean you made the remark that if you have norm inequalities for the ratio, then you can recover hypercontractivity using that argument. Right. By the way, I had a question about that part, but maybe I will ask at the end of the talk. Okay, I think I will ask at the end.
Okay, sure. Great. So let me now sketch a proof of the main result. Right. So we're interested in this maximal ratio of the piece norm and the second norm over all homogeneous polynomials. Homogeneous polynomials are just functions whose Fourier transform is supported in the Hamming sphere of radius d. Right. And note, please, that I raise this ratio to the power p. Instead of looking at the ratio of the norms, I raise the norms to the power p. Right. So we want to show that this ratio is bounded by this exactly the same bound we had before, but since I raise to the power p, I multiply the exponent by p. And I call this p times phi by a new name psi. Right. And let's define by little r of n, d, and p the same ratio for the Kravchuk polynomials. And the key step is to show that these two ratios are not very far from each other. In fact, the capital R, the maximal possible ratio, is bounded by some sub-exponential factor times the little r of n, d, and p. And given that, the main claim will follow by tensorization, which will kill the sub-exponential factor. Let me not go into it. In fact, this function psi is obtained by taking this ratio for the Kravchuk polynomials and applying this tensorization argument. So we are looking at tensor powers of the cube of dimension n. We get at m's power, we get a cube of dimension n times n. And the degrees increase correspondingly, and then we take the m's root. Again, this is just a very vague, very hand-waving thing. But basically what I want to say, I want to prove 2 and not 1. Okay, so I want to have this, I allow myself a sub-exponential error. So we'll prove 2 by induction on n. And we may assume, because we allow this exponential error, that d is not too close to the, to the endpoint of the interval it lies in, not to 0 and not to n over 2. Okay, so we want to show this. This will follow from the two following claims by induction argument. Proposition 1, we have this explicitly defined function capital F, which depends on p, of two non-negative variables. Importantly, we have this inductive. I'm looking at the second claim of the proposition, that if I look at this maximal ratio for polynomials on the n+1 dimensional cube, polynomials of degree d, this maximal ratio is bounded by this explicit function f, which I apply to two parameters. The maximal possible ratio for polynomials of degree d on the n-dimensional cube and of degree d-1 on the n-dimensional cube. Is this okay? I mean, there are many letters. Fine. Is it clear, the sort of the inequality I want?
For me, it is clear.
Okay.
Yeah.
Okay, great. So, and also we want this function f to be one homogeneous, right? If I, multiply both x and y by 2, it's increased, correspondingly, and it's also to be increased in increasing in both x and y. I will define this function. Right, so this is the first proposition. This is sort of the easier part. The function will be ugly, and actually this is the easier part. There is a key step inside of this proposition, and we get a rather ugly function, which you'll see. And then the second proposition is that this in fact, this inductive inequality holds almost with equality up to some small error for the Kravchuk polynomials, for the KDs, right? Recall that the little r is exactly this ratio for the Kravchuk polynomial. And for this polynomial, this holds almost with equality. If we have these two facts, then by induction, we can prove the main result. We obtain a sub-exponential error. Does this seem reasonable?
So when you iterate this, you go a little bit down, right? You will reach RDDP at some point, right? And how you want sum bound or on RDDP, right?
Right, but please remember that I know, as I said, this is trivial. As I said, I can assume that D is bounded away both from 0 and from n over 2. This is because I allow sub-exponential error. When I get to
okay, yes, you're right. So,
too far down, I'm fine. Right. Okay. So this is what I want. This is what I want. And in fact, the second proposition is harder technically, but I won't prove it because it uses many facts about Kravchuk polynomials. So many non-facts and some new facts. These are orthogonal polynomials, of discrete variable, classical ones. And and one knows many things about them. And again, I won't talk about this. So from now on, I will focus on proposition 1. So let f be a homogeneous polynomial of degree d, which attains this maximum that we want. Right now, we want to take the the inductive step. We split the n+1 dimensional cube into 2 n-dimensional cubes according to the last coordinate. Right, and fi is a restriction of f to each of these 2 cubes. Now it's very easy to see. It's a very easy fact, basically related to to properties of the harmonic basis on the one-dimensional cube. So there are homogeneous polynomials of degree d and d-1 over the n-dimensional cube, such that the restriction f0 is the sum of these polynomials, and the restriction f1 is the g0 minus g1. This is like a very simple thing. Great. So we can write, given this, we can write the ratio of the norms of f, of the moments of f, via these 2 functions, g1 and g0 and g1, just by substitution. There is nothing here. Nothing is done here. And here comes the key step. So we have this, and here comes the key step. This is the Hanner's inequality, which says the following: for any 2 functions, we have the following inequality. What's interesting for us, what's useful, that know that the left-hand side has these norms of linear combinations of GIs, but on the right-hand side, the norms are separated out, right? We have only the normal G0 and the normal G1, and that's why we can apply the inductive step. So substituting using the induction hypothesis for G0 and G1 and simplifying, we get this. So using the inductive hypothesis that their ratios are smaller than this capital R of NDP and R and D-1P. But the question is, what function f do we get? And let me describe you, do use the function f. So the function f is a function of 2 positive parameters, x and y. Let rho be their ratio, x over y to the power 2 over p, depends on the norm p. And let p of z be this function. It's a function of z. It's slightly ugly, but not too ugly. And then f is this following expression: f of x and y is y multiplied by the supremum over all non-negative b's of this ratio. This is the function f we get from this argument. I mean, you just substitute Hanner's inequality and you clean everything out, you use the inductive hypothesis, this is what you get. And this is a function we want to prove the second proposition for the Kravchuk polynomials, right? And luckily, this holds. So the Kravchuk polynomials satisfy this inequality for this function f almost with equality. And in particular, note the following intriguing fact: that for any p larger than 2, and for any sufficiently larger n and d, these 2 adjacent Kravchuk polynomials, 2 orthogonal polynomials, kd minus 1, kd, satisfy Hanner's inequality almost with equality. So Handel's inequality, as far as I understand, measures something like uniform convexity, quantifies something like uniform convexity of the LP spaces. And this says that these two adjacent orthogonal polynomials are almost extremal for Handel's inequality. Now, for me, this is very intriguing, and this should hold for any P. And again, this seems like a phenomenon which I would be happy to explain better. And maybe this holds for all, for many classical families of orthogonal polynomials and so on. Then I don't know. Particularly this holds for Crotrix.
For any P, you mean P also less than 2?
No, larger than 2. Larger than 2.
Larger, yes.
Larger than 2. Right, and I think I'm done. Okay. Yes.
Okay, thank you very much.
Sorry,
Alex.
I'm slightly over time, but I apologize. Yes.
No, that's fine. Thanks for the great talk. I very much enjoyed your talk. Let me ask a few questions. At some point, you said there is this folklore that if you have this moment inequalities with P minus 1 divided by Q minus 1 to the power D over 2, you can recover hypercontractivity.
Right.
But this inequality you have for homogeneous polynomials, right?
Right, but then you sort of sum over. You use triangle inequality and tensor. Use triangle inequality, you get some extra factor of n or something, and then you use tensorization and remove this factor.
So are you saying that you can prove that inequality for polynomials degree D?
If you prove it for all D, then you can recover hypercontractivity. This is equivalent.
But if you have that inequality for polynomials of degree D, not necessarily D homogeneous, in that case you can recover, right? Or you only need homogeneous?
No, but also for homogeneous. But also for homogeneous, because you get some error, which is sort of definitely sub-exponential, like linear in n, and then you can remove this error by tensorization.
Okay. One more question. You had this conjecture in coding theory where you had that if you take supremum over all functions whose support is in AD, L4 norm divided by L2 is bounded to the little o of n.
Let me
you had
yes, I like this
L4 because this even powers because it coincides with that fact because you can open parentheses and
right. So you can write it for any two norms. Just F4 over F2 are the easiest.
Okay.
So you can any like if you can prove it for any two norms, this would be sufficient.
Yes.
But again, I have taken 4 and 2 just because these are the easiest. Because this is combinatorics and not not analysis.
Okay.
Right, because you can, as you said, you can raise it to the fourth power, and then it just counts sort of count things. This is the counting expression.
I see. Okay, so if you prove for any ratio of two norms, then it also implies then the bounds can be improved this corollary. Okay, so this 4 and 2 is not important, right?
No.
Okay, I see. And there is also a version of Handel's inequality for n functions. But
you mean for many functions? But right, so then presumably this would be interesting if one can also look not at 0 1 to the n, but 0 q to the n. I guess 0, but I mean by a larger cubes or something.
Yes, when you decompose like gu0 plus g1, you have many x1. Okay. Does anybody else have any questions?
No. Thank you for the talk.
Yeah, sure. Happy to.
Well, then I will stop the recording.
Yeah. Okay, great.